We now introduce the concepts of cohesion and adhesion. And if you've had a chemistry course, you've probably dealt with these already. Attractive forces between molecules of the same type are cohesive forces. So cohesion is when a water molecule wants to bind with another or stay close to another water molecule. Attractive forces between molecules of different types are adhesive forces. So one type of molecule wants to adhere to another or stick to another type of water molecule. So both of these forces, the only difference is cohesive forces are molecules of the same type wanting to stick together. Adhesive forces are molecules of different types wanting to stick together. So if you can imagine the adhesive and cohesive forces of rain on a newly waxed car. As the raindrops fall on a newly waxed car, or say you use Rain-X on your hood, your windshield, as water droplets fall, if you don't have a newly waxed car, or you have a standard glass surface, water droplets will stick to the windshield, right? They will stick to the car's paint. The more wax you have, the shinier your surface, the smoother your surface, the less likely those raindrops are to stick to the surface of your car, the less the adhesive forces between water and the wax on your car. But the water molecules still have cohesive forces. They form little drops. Now those little drops, those little circular drops, are due in part to surface tension. Now surface tension is caused by the cohesive forces between molecules in a fluid, causing the surface of that fluid to contract to the smallest possible surface area. So if you've ever looked at a graduated cylinder and you've talked about the meniscus on that cylinder, that's a combination of the adhesive forces of the water reaching up. So if you look at a simple cylinder, let's go over here, sometimes you can see a meniscus form. The raising, rather than a perfectly horizontal line, you'll actually get a raising in near the edges. That's due to the adhesive forces from the water on the side of the graduated cylinder. If the cohesive forces are stronger, you can actually have something that looks a little like this. But that's typically not seen. You end up with this situation. That's the meniscus you would have on the surface of water or some kind of a fluid in a graduated cylinder. Surface tension is what allows insects, water striders, to walk over the surface of water. It's what allows a pin, which is made of dense material, to actually float on the surface of water because of these cohesive forces. So we will look a little bit more detail at surface tension. Looking more closely at the surface tension, we see that surface tension, which is represented in your book by a lowercase gamma, is the force per unit length provided by the cohesive forces creating the surface tension at the top of a fluid. So surface tension is force per unit length. Now surface tension, your book goes on to describe, can create bubbles on a surface. It's the surface tension trying to pull those cohesive forces trying to pull together, trapping air inside and creating a bubble. Inside that bubble, there's some pressure. We can look at the gauge pressure. Inside these bubbles, from the following relationship. So your book describes the pressure, the gauge pressure inside a bubble, so this is the pressure above the atmospheric pressure, is equal to 4 times the surface tension over R, where R is the radius of the bubble. So think of the large soap bubbles that you can create when you add detergent to a sink of running water. Normally without that detergent, right, when you have the water running, just water, after you turn it off, you have a sink of still water, no bubbles. But you add detergent and then turn on the water. Air gets trapped inside those bubbles due to the effect that soap has on the adhesive forces of water. And you can then create very large bubbles. The larger the bubble, the bigger R is, the lower the gauge pressure is inside of that bubble. So small bubbles have a much higher pressure than large bubbles do. And then finally, discussion of fluids. In this section, we come to capillary action. And you've probably all experienced capillary action. If you've ever worn long pants on a wet day and you feel the water creeping up your pant leg. Or if you dip the corner of a washcloth or paper towel in the water and you can see the water appearing to defy gravity rising up inside of that capillary tube. Well, you need a narrow tube for this capillary action to work. And in the case of clothing, it's the fibers that act as it's gaps between the fibers that act as narrow tubes. Inside the paper towel, it's the gaps between the paper, right, that makes up the paper towel. Trees use capillary action to bring water up to leaves. There is no active pump within a tree, so the water that the tree gets from the roots is pumped up through cell walls, basically adjacent cell walls, in a capillary fashion to get up to a high tree. So capillary action is due to the adhesive forces within a fluid. If the fluid had no adhesive forces, it didn't stick to the wall, that meniscus that we drew earlier didn't exist, then capillary action would not be possible.